So welcome everybody to this month's Spatial ML seminar. For this talk, we have Mohamed Elgammal. He's actually one of the team members of our research group in University of Toronto. So Mohamed is a PhD candidate at the University of Toronto under the supervision of Professor Von Betz. He really likes to do research in FPGA CAD tools, FPGA architecture, and how to use reinforcement learning in CAD. He received his bachelor and master's degrees with honors in electronics engineering from the Cairo University in Egypt in 2016 and 2018, respectively. And he's an affiliate of the Intel VMware Crossroads 3D FPGA Academic Research Center, and also the Center for Spatial Computational Learning, which is Spatial ML. And today he will talk to us about the interesting ways that he studied on how to incorporate reinforcement learning and machine learning in FPGA CAD. So Mohamed, floor is yours.
Thanks, Andrew. So hello, everyone. And yeah, as Andrew said, today I'll be giving an overview over the work I've done through my PhD, aiming to increase FPGA CAD adaptability and quality using various techniques, including reinforcement learning. So here is the agenda for my talk today, and I'll start with some motivation and background. So FPGA device sizes are increasing. For example, Xilinx has an ultra-scale device with 9 million logic cells, and Intel has a Stratix 10 GX device with more than 10 million logic cells. Concurrently, the FPGA fabric is becoming more complex by integrating more heterogeneous blocks. For example, the tensor blocks in Stratix 10 NX, or the hard knock and adaptable engines in Versal Xilinx device. Both of these factors pose great challenges on the FPGA CAD flow, causing longer runtime and also longer development time to develop the modern CAD tools that can keep up with the architecture evolution. But like a quick overview, what is the FPGA CAD flow? So FPGA CAD flow is responsible of taking a high-level behavioral specification in some kind of hardware description language and maps it to a low-level implementation, producing a bit stream that can configure the FPGA to implement the given design using a variety of algorithms and tools. So the whole flow should adapt to the architecture evolution. So either you should keep updating your algorithm with every architecture update, which is time-consuming and will be very challenging, or your tool should have another input that describes the architecture and be clever enough to adapt automatically. And to manage the complexity and be able to track and control the runtime of the flow, it's usually divided into stages. So first, the design is synthesized, converting the behavioral description of the hardware needed to a set of optimized logical hardware operation. And then these operations are mapped to the resources available in the target FPGA device in the technology mapping stage. And then the technology map netlist is packed together in a larger blocks of the target FPGA device. And in placement, we find a location or the optimal physical location for each placeable block of the netlist. And finally, routing is responsible for establishing the connections between the pins of the netlist by utilizing the prefabricated routing wires and programmable switches on the target FPGA. So splitting the flow like this into steps helps in managing the complexity and controlling the runtime, but it also limits some global or limits the opportunity for global optimizations. So there is some trade-off here between like allowing more collaboration between the different stages or controlling the runtime. So in this talk, we will focus on like different optimizations we proposed for packing, placement, and like packing placement stages, or like the way to operate packing and placement stages. A quick overview over like one well-known placement technique, which is simulated annealing, that's widely used in different FPGA placers, some commercial ones like Quartus, in which it's actually used with analytical placers, or some widely used commercial open source tools like VPR, in which it's used as a standalone placer. So simulated annealing is based on the idea of annealing in metallurgy. It starts with initial placement, then it modifies the placement by making perturbations or swaps that we call moves. Then it accepts or rejects the proposed moves based on the change of cost. It also allows some moves that degrade the placement cost to be able to escape local minimum, and it controls the whole process using the temperature notion. In VPR, which is the platform or the baselines that we implemented all of our ideas on, it only supports fully random moves, which randomly swap things that are compatible. So maybe a logic block with another logic block. And as the solution space is very large, this can take a very long runtime. So people have come up with some heuristics to make this better, such as range limiters, for example, which means I initially allow things to swap to a very far part of the device. But as the optimization progresses, I only allow small changes to get more effective moves and convert to good moves quickly. But like the question was, can we do better than that? Can we make smarter moves that efficiently explore the solution space? And yeah, here come our first contribution, which is directed moves. So in directed moves, we are trying to exploit some information that we already know about the circuit and circuit structure and timing information. So we actually do know a bunch more information that we are just ignoring when we do random moves. So we can look at the connectivity of the circuit and see that like these blocks are all connected. So instead of trying random moves of the blocks, we should propose that the yellow block to be moved somewhere near the blocks it's connected to. So we implemented multiple directed moves trying to optimize wire length, timing, or even post timing and wire length simultaneously. One example of the moves that we proposed and implemented in VPR is the feasible region move. So in this example, we are trying to move the blue block here, which is connected to multiple inputs, the green blocks. Some of them are timing critical, which is the dark green, and it's also connected to one output, which is the red block here. So we're trying to place, or we are using the information that placing a block inside the minimum bounding box that's including its critical input, the block itself, and its critical or its most critical output should be minimizing the delay of this connection, the input block output connection. So we are trying here to find the intersection of the different bounding boxes for the different critical inputs for this block. So each dotted line is a bounding box of one critical input, a block, and its output. And then the yellow highlighted region is the intersection of all these blocks, which is the feasible region for this block. So moving the block anywhere inside it should actually enhance the critical path delay. We proposed multiple directed moves. I will not go into the details of their algorithms right now, but like here is a summary of them. So we preserved the random moves that was already in VPR, different versions starting from VPR 1 up to 8 to ensure diversity in our solution. We also proposed two moves that target wire length optimizations, which are median and centroid moves. And we proposed two moves that target timing optimizations that are critical, random, and the feasible region. And we proposed two moves that target both wire length and timing optimization simultaneously, which are the H-weighted median and weighted centroid moves. Our second contribution is RLPlace. So once we proposed the various directed moves, we faced some question on how to select these moves to efficiently explore the solution space. So what should be the frequency of the different move types? And should this schedule be static throughout the different states of the anneal, or should it be changing with the circuit characteristics or the FPGA architecture? And to come up with this schedule with any CAD algorithm, usually the process of like implementing a CAD algorithm is starting with an idea based on some intuition of the CAD engineer, and we implement this idea into our tool, and you evaluate it on a bunch of benchmarks, aiming to get a good result. But usually this doesn't happen directly. Usually the results aren't very promising. So we should keep tuning our algorithm over and over and our parameter until we come up with a set of parameters, an algorithm that actually works good for the average case. So we test on a bunch of benchmarks, and then we try to enhance the average results. So in this thrust, we try to actually get human out of the tuning loop and use a reinforcement learning agent instead to actually be part of the loop. And instead of having a static schedule for the different move types, we can have an online or dynamic adaptation for which move type to be chosen for every annealing state, FPGA architecture, or circuits to be played. So we formulated the problem of move selection as a reinforcement learning problem by having a reinforcement learning agent that can take an action, which is one of the different move types that we proposed in the directed moves. And then the simulated annealing will evaluate the move, apply it, and decide whether to accept or reject it. And then send the agent a feedback, which is a 2 piece of information, whether this move was accepted or rejected, and what was the change of the placement course. The agent should actually use this information to update its knowledge and take the next action. So the agent is only learning online from the current placement with no knowledge, with no pre-knowledge from offline training. And it's adapting online to what's happening throughout the anneal and based on like the current optimization progress. So let's see how this affects what's the agent choices inside the agent. So this graph is for one of Koios 2 benchmark circuits, which is brainwave. It's showing the number of moves that the agent selects for every move type for the different annealing temperatures. And as we can see, the agent starts selecting all the move types pretty much with the same probability. But after some exploration, it learns that some moves is actually more useful than others. So it focuses more on uniform weighted centroid and median moves. But later on, it found that like median ran out of ideas. Let's now add more random or uniform moves. And later on the second state of the anneal, it actually started to enable more moves that actually focus on timing, such as weighted median or critical random or feasible region. So this graph shows that like the agent was able to change the move selection schedule throughout the different stages of the anneal. Now let's compare what's happening inside the agent for 2 different circuits. So the graph on the right is for stereo vision 1, which is one of the VTR benchmarks targeting Stratix 4-like architecture. And as we can see, the agent choices are actually totally different on the graph on the right compared to the one on the left. So in this case, it actually preferred to have more random or uniform moves, and later it preferred more feasible region moves. So this shows that like the agent doesn't only adapt to the different stages of the anneal, but it also adapts to the different FPGA architecture and the different circuits to be placed. To measure how this affects on the overall results of the placement, we compared RLPlace, which is our reinforcement learning based placement technique, compared to VPR8, the latest VPR placer. And to get a full runtime quality trade-off, we actually take one of the parameters that controls the runtime quality trade-off of the VPR placement, which is the number of moves to be done per temperature. We sweep this parameter to get a whole curve for VPR runtime quality trade-off like this. And we did the same for our reinforcement learning-based placer RLPlace. As we can see on both the wireless graph on the left or the critical path delay on the right, RLPlace curve is well below the VPR8 curve, which can be interpolated as in two ways. First, if we draw any vertical line, we can see that like in RLPlace, we are able to achieve better results or like lower critical path delay and wire lengths on the same runtime. Or if we draw any horizontal line, we can see that like RLPlace would be able to achieve the same quality of results, wire length or critical path delay in half or less than half the runtime. To exactly quantify this, we compared the default runtime point results for both RLPlace and VPR8, and comparing it on even a different benchmark suit, Titan benchmark, and averaging over 3 different seeds, we can see that we are able to achieve the same wire length and almost the same critical path delay in only 44% of the runtime. Now let's move to RLPlace. So we want to have even more intelligent reinforcement learning agent. So we expanded the action space so that the agent can control not only the move type to be chosen, but also the block type to be moved using this move generator. So instead of having an action space of size of n, where n is different move types available, we expanded this action space to be n by k, where k is also the number of block types available in the placed netlist. So to compare what would be happening inside the agent for RLPlace 1 compared to RLPlace 2. Let's see this graph, which is showing the number of moves that's trying to move a CLP block throughout the different annealing temperature, or IO blocks for the different annealing temperature for Stereo Vision 0, which is one of VTR benchmarks that only has IO and CLP blocks. As we can see here, the ratio of moving a CLP to IO is constant throughout all the different temperature in the first state of the agent. And this is because the agent is just picking the moving block randomly. And because this netlist have CLP double of the IO blocks, it's actually moving CLPs double of moving IO blocks. On the second stage, when we are focusing more on optimizing timing, the agent is, or the move generators are actually picking the moving block between the highly critical blocks. And that's why it's still, the ratio is still constant inside the second state, but it's a bit different compared to the first state. However, in RLPlace 2, the agent isn't just learning which move type to be used, but also the block type that should be moved in this state of the anneal. That's why we can see the percentage of moving IO blocks compared to moving CLP blocks is changing throughout the different annealing temperature. So at some point, the agent figured out that like moving IO is more beneficial right now, so let's focus more on moving IO blocks. But later in the anneal, it found that it become less beneficial, so let's now lower the percentage of moving IOs and focus again on moving CLP blocks. Now, how is this more flexibility or more controllability of the reinforcement learning agent mapped to the overall results? So in this table, we are showing, or we are comparing RLPlace 2 to RLPlace 1 on various benchmark suits on the default runtime point. And as we can see, for VTR benchmarks, for example, RLPlace 2 was able to achieve 5% less wire length, 3% less critical path delay, while reducing the placement time by around 30%. These results are consistent for various benchmarks, or even larger for the Koios 2 benchmark, which focuses more on deep learning workloads, where we were able to achieve 80% less wire length, 8% less critical path delay, and cutting the runtime of RLPlace 1 to less than half. To further test the robustness and adaptability of RLPlace 2, we compared it to RLPlace 1 when trying to place NOC synthetic benchmarks to target an FPGA with hard NOC routers. So we added some NOC metrics to the placement cost, like aggregate bandwidth and latency. And this graph is showing like a three-way comparison. First, RLPlace 1, which is our baseline here. But we found that in RLPlace 1, we very rarely try to move NOC routers because they are an appended resource in the netlist. And we are only picking the moving block randomly. So the probability of moving a NOC router was very low. So we had a different variations of RLPlace 1 where we hard-coded a 40% forced router moves. So 40% of the time, the agent will be forced to move a NOC router. And in this case, which is the red column, we were able to achieve the same wireless and the critical path delay as RLPlace 1. We were able to reduce the aggregate bandwidth by 4% and the latency by 38%. However, this comes at the cost of increasing the overall place time by around 50%. Then RLPlace 2, with no hard-coded at all for the NOC router, we're able to achieve the same wireless, was able to enhance the critical path delay by 2%, the aggregate bandwidth by 6%, the latency by more than 40%, while actually cutting the runtime of RLPlace 1 by 50%. So this shows how RLPlace 2 can adapt more to like new introduced placement, new introduced blocks like NOC routers. The last contribution I'll be like talking about today is the reclustering API and its applications. So let's quickly see how packing and placement stages are cooperating to produce a place design in different tools. So first for VPR, which is our baseline, packing is performed first, and the resultant packed netlist is immutable. It's passed to the placement engine where we can only place clusters. This complete separation between packing and placement stages reduces the problem size, but it also makes it easier to handle the complex design rules of modern heterogeneous FPGAs, which makes the flow very generic, can target arbitrary architecture. However, this complete separation leads to suboptimal solution due to the lack of global optimization, because in placement we are very limited. We can't actually change the packing decisions that were made earlier in the flow, only based on the logical connections. A whole bunch of different ideas to break the boundary between packing and placement stages were proposed in different work, and they reported promising quality of results. However, to do so, most of them only deal with logic blocks and neglect important blocks like carry chains, and they use simplified architecture with pre-packed RAM and DSP blocks. Although there are a lot of interesting ideas and algorithms here, they aren't broadly applicable because all of the shortcuts they make. The goal of our work of this trust is to break the boundary between packing and placement and allowing flexible reclustering technique to preserve the architecture flexibility while allowing more flexible optimizations. So to do so, we propose the reclustering API, which is a flexible API to be able to modify the packing decisions anywhere in the flow during packing or placement. And the API keeps the solution legal with every change, so no need for further legalizer. It also supports arbitrary architecture, and we try to make the API calls as fast as possible by using fast legality checker, which is a pin feasibility that actually counts the number of available pins at every level of the hierarchy and compared to the required pins by the netlist. The API has three different interfaces. First, an interface that able to remove a primitive or a group of primitives from an already packed cluster and create a new cluster for it. Like in this case, moving this flip-flop from its own cluster and create a new cluster for it, which is CLP2, or moving a primitive to an existing cluster. So in this case, moving the flip-flop from CLP1 to an empty location, CLP0, or swapping two molecules or two groups of primitives between their own clusters, like swapping the lookup table flip-flop pairs between their clusters, CLP0 and CLP1. So these three interfaces will allow the user to use to propose any change to the already packed netlist, either in packing or placement. So this API can be used in various ways, or like to propose various optimizations. First, it can be used with an semi-legal global placement, which there are a lot in the literature, to build the legalizers that can take this semi-legal global placement and try to build a fully legal one by taking one cluster output of the semi-legal placement, try to create it at primitive by primitive, and once it's legal, commit it. If not, the legalizer algorithm should find a way to legalize it while minimizing the disruptions to the global placement solution. Or it can be used to optimize VPR flow by introducing a more flexible flow. So in this graph, we are showing the traditional VPR flow in blue, starting with a packing, which is only an initial packing solution, a greedy packing one. Then an initial placement, which is a random or better than random initial placement. And then a CLP placement based on simulated annealing moves that can only place whole clusters. Then using the reclustering API, we can improve or increase the flexibility of this flow by adding three different optimizations. First, packing improvements, where we iteratively improve the initial packing by trying an iterative technique. Or after the initial placement is done, we can have some placement-aware packing improvements. Or during the placement, or even after it, we can allow some directed moves that can not only place whole clusters, but even place a single lookup table or lookup table flip-flop pairs. To test the reliability of the reclustering API, we implemented the first use case, which is packing improvement. So we used the flowchart on the right to actually spend some runtime budget that the user can give us after the initial packing is done, trying to further optimize the packed netlist by proposing a swap between some primitives, evaluating it, and then if it's good move, apply it using one of the interfaces of the reclustering API. And by applying these techniques and using multi-threading to reduce its runtime or its runtime overhead, we were able to achieve or to optimize the wire length by almost 1%, the critical path delay by 1%. And although we increased the overall pack time by 9%, because now we are adding one more stage after the initial packing is done, the overall flow runtime, which includes packing, placement, and routing, slightly was reduced, because now the quality of the packed netlist increased. And yeah, the same happens for the memory. Also, like the memory footprint for the packing increased, the memory footprint for the overall flow stayed the same. So this shows that like we were able to, by applying the reclustering API, using it to iteratively improve the packing solution, just after the initial packing is done, we were able to achieve the wire length and the critical path delay almost at no cost on the overall runtime and memory footprint. So conclusion, so in throughout my PhD, we proposed like RLPlace 1, where we propose multiple directed moves and a reinforcement learning agent to intelligently select the move type. This lead to 2x speed up for placement. We further enhanced it in RLPlace 2, where we made the agent select not just the move type, but also the block type to be used. And this proved to be more adaptable even for new blocks like knock routers, and further increase the gains on traditional ones. We also introduced the reclustering API, which allow modifying the packing decisions anywhere in the flow. We showed multiple use cases for it and implemented one of them, which is packing improvements, and we were able to achieve 1% wire length and 1% critical path lay gains almost at no cost. Yeah, that's it for today. Yeah, thanks, and yeah, any questions?